Hello and welcome to Engineering Simple. So I'll continue talking about the calculation of the line to ground faults on the low voltage side and how to calculate the current that will be flowing through the high voltage, through the low voltage, and through the delta winding. So I kind of went through the first video. I went through the objectives of the video. Then I drew the three-phase system. Then we realized it's kind of hard to deal with the three-phase. Since we're dealing with steady state, it's better if we just do a one-line diagram basically. So that's what I did here, and from here I kind of created the sequence network. So you see the positive sequence, negative sequence, and zero sequence network. It kind of set up some terminology like the occurrence, so on and so forth. I would recommend watching the previous two videos. So now I'm going to continue. So basically what I want to do, so go from here. Instead of that, I just want to simplify. Basically, I want to, okay, draw. Here's the source, kind of like Thevenin equivalent, basically, what I'm trying to do. So here's the equivalent, or it's the Thevenin equivalent positive sequence impedance. Then here's the negative sequence equivalent impedance. So there is no source in the negative, and the same thing in the zero sequence impedance, so zero equivalent. So really that's what I want to kind of establish from here, and I'll get a different color just so you see how you can connect these. So basically then you just connect these guys here, and basically since this is just one line, I0 will flow, and I0 is the same as I1 is the same as I2. So zero sequence, positive sequence, and negative sequence currents. And we will assume this voltage is 1.05 per unit. That's typical when you are dealing with short circuit calculations. So really, I did not do anything here. Basically, I just redrew these here. So the equivalent impedances basically is just a combination of the sum of these. They are in series, then in parallel with this. That's really all I'm doing here. So now we're going to calculate those equivalent. So if you go back to the original, so this this diagram, you notice, so okay, so let me just kind of, let's calculate Z1 equivalent, Z2 equivalent, and Z0. So these are the Thevenin equivalent positive sequence impedance, the Thevenin equivalent negative sequence impedance, the Thevenin equivalent zero sequence impedance. So if you go back to that diagram, you notice that here you have system A, and you have the positive sequence impedance of system A, and basically instead of breaking down the transformer positive sequence, I'm just going to write Z transformer, which really is the Z1H plus Z1X, just so I'm clear what I'm saying here. So basically, instead of writing ZH, Z1H, Z1X, I'm just writing the through just as one impedance. Because sometimes the positive sequence and negative sequence equivalent T model may not be available. You might just have one impedance basically. So then you have the terminal X here, and system B is in parallel. System B. And we said I1H current flows through here. So basically, if you go back here, really, this is all I'm doing. So you have this impedance plus this impedance is in parallel with this impedance. So really, that's all I'm doing here. So that's for the positive sequence equivalent impedance. Now I'm going to do the same thing. So from here, actually, I can go ahead and write this. So I know Z1 equivalent. So the positive sequence impedance is Z1 system A plus Z1 of the transformer. And you can write instead of transformer T, or which is in parallel. So this means in parallel with Z1 of system B. And from circuit analysis, if you have two impedances in parallel, the equivalent is just the product of the impedances divided by their sum. So Z1 system A plus Z1 transformer times Z1 system B divided by their sum, basically. Z1 system A plus Z1 transformer plus Z1 system B. So basically that's the equivalent positive sequence impedance. Now, and like I was saying, I just want to make sure it's clear, Z transformer, basically Z1 transformer is just Z1H plus Z1X, and typically in test reports you will just see Z1 basically HX, from the high to low voltage. That's typically what you see on the test report. So now let's draw. So the negative sequence impedance will be kind of similar. So you have A, you have system, the negative sequence of system A, then you have negative sequence of the transformer, which is the same as the positive sequence. So you have X, then you have system B is in parallel. And this is the negative sequence current that flows through the high voltage. So again, we'll do the same trick, the negative sequence or the equivalent negative sequence impedance. So you have Z to system A plus Z2 transformer in parallel with Z2 system B, and you do the same thing to find the equivalent, which is the product of the two impedances divided by the sum. So then we can draw the equivalent zero sequence impedance. So for this zero sequence, we have the zero sequence of system A and we have zero sequence of H, then that is in parallel with the zero sequence of Y, and we said the current that flows through this impedance, we call it I0Y. Then the equivalent of these impedances is in series with 0 X, and we had terminal X here. Then we have this, the 0 sequence impedance of system B here, and we call this I0X. So again, if you want to be like, if you want to understand what's going on, really, this is what I did. So this impedance plus this impedance is in parallel with this impedance. Then once you find that equivalent impedance, which is just the product of the two impedances divided by the sum, it's in series with this, so you just add this impedance here, then that equivalent is in parallel with this. So really that's all I'm doing here. So I would recommend going back to the diagram in case you are unsure of what's going on. So zero sequence or the equivalent zero sequence impedance. So basically we have zero sequence of system A plus zero sequence of H. So these two impedances here, the sum of them is in parallel with zero sequence of Y. So once you find that, then you just add the zero sequence of X, which is this here. Then once you find this impedance, the equivalent, you put it in parallel with the zero sequence impedance of system B. So it's a lot. So it's a lot of stuff going on. So now, basically, I calculated all the equivalent impedances. And note, so this here would be known. This would be known so this here would be from the power system. The utility or whoever owns the system would provide this impedance. The transformer manufacturer would provide this and this impedance and this impedance. The utility or power system owner will provide that. So all those are known. The same thing here, known, known, known. So all these impedances here are known basically. So known, known. So now all the equivalent impedances are known. So now we can proceed to calculating the currents. So I'll do that in the next video. Thank you for watching.